As designers deal with motion, it's sometimes necessary to change the motion from one type to another. Linear motion is motion in a straight line. Rotary motion is a spinning motion, and reciprocating motion is a consistent back and forth motion. By using different mechanisms, designers are able to convert motion from one type into another. For example, if a gaming console has a disc tray that needs to slide in and out using a linear motion, but must be powered by an electric motor that provides a rotary motion, the designer must use a mechanism called a rack and pinion gear to convert from the rotary motion provided by the spinning motor to the linear motion required by the tray. There are dozens of different types of mechanisms that can be used to convert motion from one type to another. The more you know about them, the better you're going to understand mechanics. Newton's second law of motion shows us the mathematical relationship behind forces. It states that force is equal to the change in momentum per change in time. For a constant mass, force equals mass times acceleration. The easy way to remember this is F equals m times a. If we understand the relationship between these three variables, it's possible to manipulate Newton's second law and use it to solve technical problems. For example, take a look at this Olympic thrower. In order to throw farther than his competitors, he needs to put more force into his throw. The mass of the object he's throwing can't be changed, since all the athletes must throw the same weight. So the only other way for him to increase his force is to increase his acceleration. Now, acceleration isn't just the speed that something's moving, it's how quickly something changes speed. So an object that is able to go from slow to fast very quickly would have greater acceleration than something that takes a long time to pick up speed. At the beginning of the thrower's throw, he swings the weight slowly, then moves faster and faster and faster and faster throughout the throw until he releases the weight. This increase in speed, or acceleration, is what gives the thrower so much force. Again, acceleration doesn't mean the same thing as speed. Speed simply states how fast something is moving. Acceleration refers to how quickly something changes speed. If an object is speeding up, it's accelerating. If an object is slowing down, we say it's decelerating. For the purposes of Newton's second law, acceleration or deceleration doesn't matter. We're simply talking about how quickly the change in speed occurs. Mass is the amount of matter an object has. It's a physical property of the object and doesn't change based on outside factors. People often use the terms mass and weight interchangeably, even though they don't quite mean the same thing. An object's weight is the effect of gravity pulling on mass. So if the object is moved to somewhere with less gravity, like say from Earth to the Moon, its mass remains the same, but its weight will be less because there's less gravity pulling on the same mass. Now that we have our terms clear, let's take a look at another example of Newton's second law. When you apply a force to an empty shopping cart, its mass is relatively low, so it speeds up or accelerates relatively quickly. However, if you add a bunch of items to the cart, its mass will increase, so if you push with the same amount of force, then the cart will accelerate much more slowly. You might still be able to get it up to the same top speed, but its acceleration will be less, so it will take you longer to do. If you wanted the cart to accelerate just as quickly as before, you would need to apply more force. Newton's second law shows us the mathematical relationship between these three variables. Knowing how force, mass, and acceleration affect each other allow us to get creative and manipulate these variables in our technology. In the example of the hammer thrower, he can't change the mass that he's throwing, so he must increase his acceleration in order to increase the force of his throw. In the example of the shopping cart, if you push with the same amount of force, but the mass of the cart is increased, then the acceleration of the cart will be less. Let's see a real-life example of how engineers use Newton's second law to design a clever solution to a common problem. Just a few decades ago, cars were not designed with safety in mind. They were made to be heavy, strong, and durable, So when cars got into crashes, the car usually sustained little damage, but the passengers inside suffered terrible injuries. So car designers had to come up with a way to reduce the amount of force felt by the passengers in a car accident. One strategy was to reduce the mass of the cars by using lighter materials. This also helped lead to better fuel efficiency, but there's a limit to how light the vehicle can be, so eventually the mass can't be reduced anymore. This means that to reduce force, designers needed a way to decrease the acceleration, or in this case the deceleration, of the crash. In other words, find a way to make the crash take longer. If a car comes to a complete stop in just 1/4 of a second, that means that the passengers feel all of the force of the crash in a very short amount of time. If designers could find a way to extend that crash to a half a second or 1 whole second, then the force of the impact would be spread much farther, reducing the amount of force the passengers feel in the crash. This clip shows us how one car company creatively solves this problem.
The front structure of the new Volvo XC60 was designed to distribute collision energy over the entire car body in order to absorb the forces as effectively as possible and reduce personal injury to the occupants. Volvo's patented front structure is divided into zones, each of them with a specific role during the deformation process. The different properties have been achieved by using different grades of steel, making the outer zones softer than the inner zones and ensuring that the collision forces are absorbed in a controlled and efficient manner, in order to minimize intrusion into the passenger compartment. The engine also contributes to effective deformation due to its space-saving transverse installation, and that all main components in the engine bay have their own predetermined positions, even after a frontal collision, in order to help reduce component intrusion into the cabin and provide the occupants with optimum protection.
When the car is in a crash, it doesn't stop all at once. Different parts of the front of the car are designed to crunch and collapse strategically in a certain order to slow the car down and cause it to decelerate more slowly. Lowering the acceleration helps reduce the force of the crash, so every tiny fraction of a second that the crash can be extended could mean lives saved. In this small-scale experiment, I'll be measuring the impact force of this vehicle that uses a tennis ball as a crumple zone. This vehicle crashes with about 13.5 pounds of impact force. These other spikes indicate that the car bounced back. As we can see, the tennis ball does deform on impact, but it doesn't absorb the collision energy. Instead, it bounces back, causing the passenger to experience multiple forces instead of just one. Next, I'll try this vehicle, which is designed to have about the same mass, but that uses syringes as a crumple zone instead of the tennis ball. This time, the car crashes with about 8.5 pounds of effort force, and there's very little bounce back. It looks like the syringes caused the car to decelerate more slowly, which had a noticeable impact on the amount of force the passenger experienced in the crash.